Thank you.
Thank you. All right. So the topic of today's presentation, as we said, is quantum computing and Bitcoin. So first of all, we'll talk a bit about what quantum computing is. So quantum physics is an area of physics that started developing around the early 20th century. So the fundamental idea behind quantum computing is this idea of uncertainty. So if you have studied physics, you might have heard of Heisenberg's uncertainty principle, that you can't tell the exact position and momentum of a particle at the same time. So if you try to measure the position, the momentum becomes more uncertain, and if you try to measure the momentum, the position becomes more uncertain. No matter how good your measuring tools are, you cannot know everything about a particle. And in fact, here's a more recent finding. Now, at first, when we discovered this, what physicists thought is that, okay, because particles still do have some position and some momentum, like they have to, but we just can't measure it. As it turns out, particles do not even have an exact position and an exact momentum, so an exact velocity. And there's a theorem called Bell's theorem, which uses some clever math to show that the effects of quantum physics cannot be explained by any kind of hidden variable theory. So if a particle does not even have an exact position, or an exact speed, or an exact momentum, what does it have? Well, essentially the answer is that a particle is in a superposition. You may have heard of Schrodinger's cat thought experiment, where you put in a radioactive particle into a box, and then you put in a poison pill in the box, which activates only if the radioactive particle decays. And if you close the box, you don't know what's happened. Did the radioactive particle decay? Was the poison released? Is the cat dead or alive? As Schrödinger pointed out, until you open the box, the cat is both dead and alive at the same time. That's called a superposition. All particles are in a superposition. You're in a superposition over many different states at the same time. Now, what is a Now, in quantum computing, we don't necessarily care about these sort of more fine-grained superpositions, where we don't care about all the infinite number of different states that a particle can be in. What we generally care about are superpositions over a small number of states. So, for example, we might have a particle, an electron, that's in a superposition of being in a lower orbital or in a higher orbital. So lower energy state or high energy state. So here is the common mathematical way of representing a superposition. So we have psi is some factor of 0 plus some other factor of 1, and just say it's these two things added together make up the superposition of psi. And by the way, if anyone at any point is confused or have any questions, feel free to raise your hand, because this is a very technical topic. Is everyone following so far? Sure.
Is this an atom?
Yes, this is an atom.
What do you mean by factor of 0 and factor of 1?
So here 0. This is just notation. The 0 represents the low energy state, and the 1 represents the high energy state. So 0 and now there are many different ways so this is essentially called a qubit. It's a bit, but it's stored in this quantum form. So 0 and 1 are arbitrary. You can call them alpha and beta. You can call them cat and dog, whatever you want. So next there's this concept of measurement. So you can take a superposition and you can measure it. And what measurement means is that the superposition essentially collapses. It either collapses into what you have on the left, or into what you have on the right. So at first you have a superposition of left plus right. Half the time it goes to left, half the time it goes to right. When you open the box, when you don't open the box, the cat is dead and alive at the same time. When you do open the box, you see the cat, it's either dead or it's alive. Now, the interesting part of quantum physics is this idea of quantum entanglement. So sometimes you could have particles that are in superpositions that are correlated. So what does that mean? It means that essentially, if you measure one particle, you're affecting the other. So here, for example, you might have, this is called the Bell state. So you have one half being in the state of 0, 0, and one half of being in the state of 1, 1. Now, why is it 1 over square root of 2 and not 1/2? It's a very technical mathematical reason behind it. At this point it's better to think of it as being 1/2 here and 1/2 there. So when you actually measure it, now you can measure even one particle. So you might measure the first particle. If you measure the first particle and you see 0, then the second particle collapses just automatically collapses to 0. If you measure the first particle and you see 1, then the second particle also collapses to 1. So in this way, you can essentially share information over long distances. But at this point, we don't really need to share information over long distances. What we're interested in is using this principle to do computing. So in quantum computing, as we saw several slides earlier, you can use any kind of physical states, quantum states, to represent a bit. Left you have 0, right you have 1. So next you can have quantum gates. Now you might know there are electric circuits, like electric circuits in computers. Electric circuits in computers are made up of gates. So you might, if you've taken logic, you might know about AND gates, OR gates, NOT gates, XOR gates. Quantum computing has gates too. So quantum gates let us manipulate bits, and you can put quantum gates together into quantum circuits. So a circuit takes an input and it gives you an output. So here's the nice thing about superpositions. If you take a superposition over multiple states and you evaluate a quantum circuit on it, what you're really doing is you're evaluating a quantum circuit over everything in the superposition at the same time. So why is that powerful? Because for example, say you have some problem, any problem. So for example, you have some function and you want to find the value so that the function you want to find some value such that the function applied to the value gives you 0. So what does quantum computing let you do? It lets you make a superposition of all the possible inputs at the same time, evaluate them on a quantum circuit once, and then you have a quantum superposition of everything at once. Now there's still a problem. Now there's a common misconception that after you do that, you can basically extract the information you want. So now that's not true. Quantum computing is not magic. So even though quantum computing lets you evaluate functions on every input at the same time, you still can't extract. It's still very, very hard to extract exactly the data you want. All right. Any questions at this point? Okay. So here's one problem that quantum computing can solve. Factoring. What is factoring? Now, multiplying numbers is generally fairly easy. So here you have 4-digit numbers. 1523 by 2441 gives you 3717643. For a computer, that's easy. If you personally train hard enough, you can do it too. But on the other hand, factoring is hard. So if you have 3717643, how do you know what factors that number came from? Now the simplest algorithm for that is called trial division, which is, okay, you try divide 37176.43 by 2. Doesn't work? Okay, divided by 3. Doesn't work? Divided by 5. Doesn't work? And so forth. So that's extremely inefficient. So for example, if you have a number with 1,000 digits, you're never going to succeed. There are more efficient algorithms. The most efficient one we have is called the general number field sieve. It was invented in 1991. It's still very inefficient. If you feed a 1,000-digit number into a general number field sieve, it will still take longer than the age of the universe to give you an output. So why does this matter? Because modern cryptography relies on this factoring problem being hard. What do I mean by modern cryptography? RSA, you might have heard. You might have heard of it. It's a very common encryption algorithm. Relies on factoring. For example, SSL, the protocol that secures a lot of internet connections, quite often it uses RSA. So if factoring isn't hard, then internet isn't secure anymore. So quantum computing, there's an algorithm called Shor's algorithm that can factor numbers very quickly. Now this expression here, O of k cubed, what does that mean? K is the number of digits in the number. So for example, if you have a number, let's say 2048 bits, that's about 600 digits. It's a standard size of a public key in RSA. Then quantum computing can break that in 2048 cubed steps, which is basically a few billion steps, completely trivial for any kind of modern computer. So if factoring becomes easy, lots of things will break. Elliptic curve cryptography. Now, elliptic curve cryptography is a sort of another more modern version of public key cryptography. Why did people start thinking about elliptic curve cryptography? Because of these algorithms that I mentioned, the general number field sieve. It still takes a long time, but the problem is that the general number field sieve doesn't make RSA impossible, but it does make it somewhat uncomfortable. You have to have these really big numbers. So I mentioned 2048 bits, that's 600 digits. So an RSA public key might take up just to write down on this slide, it might take it all the way up to here. So with elliptic curve cryptography, on the other hand, elliptic curve cryptography is protected by what's called the elliptic curve discrete logarithm problem. So it's a somewhat esoteric range of mathematics. Basically, the idea is that mathematicians invented these algorithms for adding together points on a curve to get other points. And you can add a point to itself many times. You can multiply a point by a number. But given 2 points, you can't figure out what number you multiplied the first point by to get the second point. And there are no good algorithms for that whatsoever. It's still very hard. So this is actually what Bitcoin uses. Shor's algorithm can also solve this really quickly. And breaking elliptic curves becomes easy, almost everything else breaks. This is the power that quantum computing has. Now, Grover's algorithm. Grover's algorithm works on any problem, literally any problem that you can define. So in the general form, it basically reverses any function. So how does it work? Basically, it runs the circuit on the superposition of all possible outputs. This is sort of the naive version of how a lot of people think quantum computing works. Problem is that doing this is still very inefficient. So instead of 2 to the k steps, it takes 2 to the k over 2 steps. In Bitcoin, for example, Bitcoin uses a hash algorithm called SHA-256. Breaking it normally would take 2 to the 256 steps, which would take so long that there literally is not enough entropy in the universe to break SHA-256 on a classical computer. On a quantum computer though, it just takes a few billion times longer than the lifetime of the universe. So it's trivial. But so quantum computing in reality, where are we now? The world record for these fearsome public key cryptography breaking machines is that a few years ago, a quantum computer managed to use Shor's algorithm to efficiently factor the number 21.
I took a quantum computing course, I think like 10 years ago, and that was still the record.
Actually, 10 years ago, the record was 15.
Alright, so they went from 15 to 21.
Yes. So the next target is going to be 35.
Yeah, okay.
Okay. Now, you might have heard of some marketing buzz from D-Wave. D-Wave supposedly makes quantum computers, Google buys them. D-Wave makes what's called adiabatic quantum computers. So adiabatic quantum computers they're not real quantum computers, okay? So I'll explain how these adiabatic quantum computers work. What you do is, first of all, you can take a problem, any kind of computational problem, and then you encode it into a bunch of magnetic needles, such that the lower the energy state of those magnetic needles, the better the solution is. So essentially, you're relying on physics to sort of naturally take all those magnetic needles and orient them in the lowest energy possible state. So essentially, you're just taking a problem and you're giving it to physics and you're saying, here, physics, do the work. So the problem with that, though, is that there have been proofs that adiabatic quantum computing is actually probably not faster than classical computing on pretty much every problem. Adiabatic quantum computers cannot run Grover's algorithm. They cannot run Shor's algorithm. They're only maybe better for some very specific cases in one very specific class of problem. So Google thinks that they might be useful for their own purposes. They are absolutely not a threat to elliptic curve cryptography.
Which problem is that? Just that. Which problems are they good for?
Okay, there is, I believe, something called the quantum Fourier transform. It's basically an operation that you can do on data to sort of discover certain types of patterns in it. I believe that's what adiabatic quantum computing might be good for. So next, we'll talk a bit about Bitcoin. So this is the technical background. This is how Bitcoin addresses work. So here you have, so everything starts off with private key. A private key is it's a number that your Bitcoin wallet probably stores encrypted in a safe location as possible. So if your private keys get out, then whoever gets those private keys can spend your Bitcoins. Keep your private keys safe to yourself. Next, there's key conversion. Key conversion takes you from a private key to a public key. So this is an elliptic curve operation. So it's essentially you're multiplying an elliptic curve. You're multiplying an elliptic curve points that everyone agrees on, called the generator, by the private key. This is a number, and you're getting another elliptic curve point, which is encoded in this format. It's a public key. Now, from there, you take the public key and you put it through two algorithms, SHA-256 and RIPE-MD160. SHA-256 and RIPE-MD160, they are what's called hash algorithms. So what is the point of a hash algorithm? They essentially input data and it makes a big jumble out of it, and it outputs that. The point of a hash algorithm is that it's basically supposed to be impossible to reverse. So from there, next you turn into this sort of special encoding. So first of all, you take the results of the RIPE-MD160, you add some extra bits to it, and then you convert that into a Bitcoin address. So the point of these extra bits is essentially what's called a checksum. So if I accidentally forget a digit, then chances are that the checksum won't match, and it's going to be an invalid address. So the point of this is basically to protect you from typos. And it works all the time except for 1 in 4 billion of the time. So hopefully nothing bad will ever happen there. So here, and this of course is the Bitcoin address, which you just give out to anyone. So once again, still any questions at this point? Sure.
Isn't this done by machines?
Yes, this is done by machines. This is what you're.
So why do you need checksum?
Because for just the checksum is just in case when you copy and paste the Bitcoin address, what if you type it in wrong, or what if you forget a digit at the end? Then the checksum is not going to match. So, how does this all fit into quantum computing? So, private key to public key conversion is an elliptic curve operation, so quantum computers can reverse it. If you have a public key and you have a quantum computer, a good quantum computer, not the crappy one that's used to factor the number 21, then you can figure out what the private key is. Public key to address conversion is it's a bunch of hash algorithms. So the only thing that you can use against it is Grovers. Grovers, once again, how long will Grovers take to reverse that particular problem? Well, over here you have 160 bits. So Grovers runs in 2 to the k over 2, so it'll take you 2 to the 80 time. How much is 2 to the 80? Well, there's about 2 to the 25 seconds in a year, maybe about 2 to the 30 2 to the 30 computational steps in a second, and maybe about 2 to the 30 years in the lifetime of the universe. So 2 to the 80 is about the lifetime of the universe. Pretty good margin. Now here's the problem though. First of all, when you send money to a Bitcoin address for the first time, the only information that's public is just the address. So if someone wants to get those Bitcoins out of the Bitcoin address, they're going to have to make a transaction and sign it with the private key. So or rather sign it with a private key that would convert into the Bitcoin address. So how hard is that? Essentially, you would need to go from the Bitcoin address up to the public key and up to the private key. First step is really hard. Now, however, if you have some Bitcoins in an address, and then you send Bitcoins from that address, and you still have some Bitcoins left, when you send Bitcoins from an address, you're creating a Bitcoin transaction. What does a Bitcoin transaction have? A Bitcoin transaction has what's called a digital signature, and it has the public key in it. So basically, the algorithm is that first of all, the miner would verify the signature against the public key, and then it would verify the public key against the address to make sure that everything matches. So once the transaction, say you create a transaction, and then you publish the transaction, and then you send off the transaction to the network. Now, imagine that the transaction gets published. Imagine that someone out there has a quantum computer. They now have the public key and they can get the private key. So if once you send a transaction from an address, that address is compromised.
Also, if you receive a Bitcoin payment into that address?
So if you receive a Bitcoin payment into a fresh address, then it's safe. But if you have an address and you spend from that address, and then you receive more Bitcoins to that address, then it's compromised still.
No, but if you receive and then receive, is the balance in that wallet now compromised? I think so. Right?
Well, no, if you receive, because receiving does not require anything from you, right?
Okay, right.
Right, so receiving would compromise just the sender. So now here's something you might think. Oh, well, what if I use every address only once? What if I have Bitcoins in an address, and let's say I received 100 Bitcoins in some address A, and then I want to send them off to address Z. Say I want to pay 10 Bitcoins to some guy for a website. Okay, I'll make a transaction, it pays 10 Bitcoins from A to X, and then I create a new address, I'll create address B, and I send 90 Bitcoins back to address B.
But then that address is also published in the network.
No, publishing an address in the network is fine. Because an address, it's just this. You can't get anything from this. What you're worried about is when this gets published.
Okay.
So this only gets published when you spend from an address.
But when I'm sending from my own Bitcoin wallet into a fresh one,
yeah. First of all, be careful not to use the word wallet. There's a wallet, like you might have many addresses in a wallet. So you send from an address, right?
Yeah.
Once you send from an address, that address is compromised.
Right.
So how many addresses can you use? Can you create them?
You can create an unlimited number of Bitcoin addresses. It's a very quick process. All you have to do is generate a random number, run through all this. Okay, so here, however, what is what I described safe? The answer is no. Say you make the transaction, then you broadcast the transaction. However, the first node that you're broadcasting the transaction to, it just happens to have a quantum computer. What can it do? It sees your transaction, it sees your signature, and it sees your public key. It takes your public key, it figures out your private key. Then, it goes into the transaction and says, 10 bitcoins to address B. No thanks, that will be 10 bitcoins to address M. And then it just uses the private key and it signs the transaction again and passes it on. So the attacker can basically just steal your money in transit. So, as it stands, Bitcoin is not safe against quantum computers. Now, your Bitcoins are going to be safe for the time being if they're in an address that you haven't spent from before. But basically, once you have sort of nodes with quantum computers, as long as attackers with quantum computers exist, you can't spend any Bitcoin securely.
Well, Bitcoins are safe as long as there aren't too many quantum computers.
Well,
right?
even
if the NSA has one.
If the NSA has one, then the NSA can steal people's Bitcoins in transit.
Yeah, but I published my transaction to a lot of nodes before they reach the NSA.
The problem with that is though. Okay, see, so yeah, so if the NSA has been so your transaction would go off.
Will be the first transaction.
It'll be the first transaction in the network, and then someone else double spends you. Okay, yes, you're right. So you are.
Yeah, but if the NSA have a quantum computer, they also have an advantage in mining.
Yes, so that's the other thing that we'll talk about.
Yes. So.
Yes. Yeah. So the NSA.
So they can put the double spend transaction into their own blocks. So.
Yes. So I'll go over what Manny just said in more detail. So Bitcoin mine. Yes.
So what happens if you do the trick that you move like 10% of your account to someone and simultaneously you move the rest to a new address?
Yeah, so the problem, right.
And you delete the old one.
Yeah, so the problem with that, as I mentioned, is that someone can modify your transaction in transit. So the transaction can get replaced with a new one going to other people, even before your original transaction gets confirmed anywhere.
Once it's done, it's okay.
No, well, once it's done, it's okay, yeah, but that'll take like 10 minutes, and that'll take 10 minutes, but every node in the network will see your transaction within a few seconds.
So when you say in transit, you mean that somebody with a quantum computer can, on the fly,
yes,
break your encryption?
Yes.
So this isn't even a matter of like waiting 2 minutes. This is like near instantaneous.
Potentially near instantaneously, yes. Shor's algorithm is O of n cubed, right? N is 256. N cubed is 16.7 million. 16.7 million steps is not hard. It's 16.7 million. And that's another 16.7 million.
That's assuming that the node hasn't transmitted the message to other nodes.
Oh yes, but the problem is that it's so fast that essentially like an attacker might be able to potentially succeed even if they succeed like 20% of the time. That's still basically on average a 20% tax on Bitcoin transactions. So it's still very unsafe for average use. So here's also, yes?
How does that compare to making a transaction to pay a credit card bill?
Okay, so transaction to pay a credit card bill. Credit card,
no, not with Bitcoin.
right, I understand. Okay, so with credit cards, your credit card information, when it passes from you to the merchant, is secured by SSL or HTTPS.
I don't mean that. I mean, let's say that you have a bank account and
Yes.
you want to pay your own credit card balance, for
Yeah.
example, and you're taking from your own bank account
Right.
money and you're paying off your balance.
Right, so here are some things that attackers can do. So once again, I mentioned that HTTPS, which is the secure internet protocol, it uses RSA or ECC. Attackers can break that. So attackers can potentially break into your internet connection when you're logging into your bank, and they can just do whatever deposits they want for you. when you're paying with a credit card, they can steal your information in transit and they can use it for whatever they want.
Yeah, so how does it compare the risk factor?
Right. So with Bitcoin, in both systems, Bitcoin isn't safe for transactions as it is, and the current financial system is not safe for transactions as it is. But with Bitcoin, it has the advantage that we know that if you store your funds safely, then you can, at least until the Bitcoin developers figure it out and come up with a solution, basically your money is safe as long as you don't move it anywhere.
But it's worthless. Because no one,
Well, but here's something that I'll get to. These problems can be worked around. You can update the protocol to fix that stuff.
Yeah, but Vitalik, but even if they do a workout for them, the funds you have in an address,
Yeah.
the attacker can still impersonate you when you want to switch to the new system. So,
Yeah, so it depends. Hold on. So you have a... Right, so you might need some kind, it depends, you might need some kind of centralization. Also, one of the protocols that I described, it actually does deal with that issue. The switchover might be a bit uncomfortable, but there are ways to make it secure. So Bitcoin mining. So what is Bitcoin mining? Bitcoin mining is essentially the process of making the Bitcoin network secure. So if you have so the rule of the Bitcoin mining is that the Bitcoin network pumps out blocks. It pumps out blocks, and blocks contain transactions. The network pumps out, on average, 1 block every 10 minutes. Right now, the first 6 digits of the SHA-256 of a block have to be 0. That's essentially a limitation that the Bitcoin network deliberately enforces to make mining hard. Why do you want mining to be hard? Because if mining is easy, then an attacker can just create billions of blocks and take over the network. You don't want that. So, first 60 binary digits, once again, so what that means is that over here, for example, here right from D160, basically you need to have here 15 zeros. So, since, as I mentioned before, SHA-256 is a hash algorithm, it's designed to be impossible to reverse. So how do you reverse it? Trial and error. You keep on trying to make a block, and you do tiny changes every time, until eventually 1 block works. How long does this take? 2 to the 60 steps, obviously. It's just keep on randomly doing it until just magically the first 60 binary digits of the hash are 0. Quantum solution, Grover's algorithm. Grover's algorithm brings it down from 2 to the 60 to 2 to the 30. So this is what Mania was mentioning earlier, which is quantum computers make very fast miners. If you have a quantum computer, you can mine faster than the rest of the network combined. And what that means is that potentially, even if Ron publishes a transaction to the entire network, and that transaction gets encoded in a block, the NSA can take their quantum computer and they can quickly mine 2 blocks. Or, well, first they'll figure out what Ron's public key is, then they make another transaction, sending Ron's money back to themselves, and then they make 2 blocks. So they just overrun the Bitcoin network, and they can steal Ron's money. So, however, what happens? So hopefully, when the quantum computer revolution happens, it'll be quantum computing for everyone. What happens in that case? Everyone has quantum computers. This should be everyone has quantum computers. Everyone has computers is what is the case today. So everyone has quantum computers. So the difficulty goes up from 2 to the 60 to 2 to the 120, because the difficulty automatically self-adjusts, and mining takes 2 to the 60 steps again. So essentially, the Bitcoin was already designed. The mining algorithm was already designed to take into account the development of faster mining technologies. So quantum computing is a faster mining technology. You can just adapt to it like anything, like it adapted to specialized hardware. Now there is one tiny snag that I actually just thought of a few days ago, which is that with Grover's algorithm, the problem if you run the Grover's algorithm for less than 2 to the 30 steps, or less than 2 to the 60 steps, your probability is actually proportional to the square of the number of steps you take over 2 to the k. So what does that mean? You run the Grover's algorithm for 100 steps, that's the equivalent of 10,000 normal steps. Run Grover's algorithm for 1,000,000 steps, that's equivalent to 1 trillion normal steps. See, this is a problem, because and the reason is that basically it strongly privileges powerful miners, because right now, if you have a miner that's 10 times as powerful, you can mine 10 times more. That's fair, that's the way things should be, right? You have 10 times more capital, you get 10 times as much revenue. With here, on the other hand, you have 10 times as much capital, you might be able to get 100 times as much revenue.
Vitalik, how easy is it to scale quantum computers? So for example, let's say I can build a quantum computer that can do 100 steps in reasonable time. So is it cheaper to do 2 of these computers than one computer that could do 200 steps?
Actually, the biggest challenge to quantum computers in practice is actually the number of bits. So right now, quantum computers 21, they can sort of maintain, probably around like 5 to 10 qubits at a time. But here, you're going to have to have 256 qubits at a time.
Yeah, but it seems to me that maybe you will also have a limit on the sequential frequency, and then even if someone has more resources, he will not be able to build a faster quantum computer. He can build maybe more quantum computers, and then it will also be linear. So,
okay, see your point. So,
like with the classical computers, we can't scale frequency much anymore. We just parallelize, and if I understand it correctly, if you parallelize, you don't get this superlinear advantage.
I see. Okay, so it depends. It's not certain that this will happen. This is a danger, but just in case, like mining, if it is possible to sort of if it is going to be true that better quantum computers are going to be faster, then mining as it is not going to be fair. So that's not a critical security issue, but it is an economic issue. So eventually, you're going to need to change it. You're going to need to change it somehow, or maybe not. We don't know. So here's how you make Bitcoin quantum safe. So here's a first algorithm, which is, this is the algorithm, by the way, that can be used to do a sort of switch over. So how does it work? First, publish the hash of the transaction. Then you wait 6 blocks. Then you publish the actual transaction. So what's the point of doing this? Essentially, suppose that once again Ron has his 100 bitcoins and he wants to send them off to some new address or to his friend or whatever. What can he do? He publishes the hash of the transaction. Then the Bitcoin protocol is going to be updated so that the hash of the transaction will go into the blockchain. 6 blocks later, publishes the actual transaction, and the funds actually get transferred. At this point, the NSA can figure out Ron's private key. But all of Ron's money is going to be in new addresses now. So the fact that everyone knows Ron's private key is irrelevant. Number 2, the NSA can't attack Ron in transit anymore, because the only thing that happens in transit is this hash. So, and hashes are, once again, they'll take 2 to the 128 or 2 to the 80 times to reverse the Clover's algorithm.
What about spamming?
Spamming, right.
Once you decouple the transaction to 2 blocks, the only one that I can just spam hashes.
Right, so like these hashes will probably need to be, first of all, these hashes will probably need to be automatically deleted after about 10 blocks or so. That's one potential idea. Another potential option is actually, what if you require the hashes to start off with, say, like 20 binary zeros? So put on some tiny proof of work on them to make it more difficult. So basically, this is just it's a sketch. Things can be done.
Can you verify the transaction just based on the hash?
No, because from the hash, from the hash, the idea is you can't efficiently compute anything about the transaction itself.
So basically, you're going to incorporate into the blockchain any hash, and you don't know even if it's a valid transaction. So
yes, but the idea is that the money isn't going to be actually transferred until the original transaction gets into the blockchain afterwards.
So it's like I don't know. It's like the first step is really null. You don't do anything there, and
no,
the actual thing happens in the end. So you
the point of the first step is that suppose that Ron publishes a transaction. The NSA gets a transaction, figures out its private key, modifies the transaction in transit. They try and include it in the blockchain. Guess what? The hash isn't in the blockchain. And so, basically from that...
Oh, I see. So in order to include a block, you have to have the hash previously.
Yes.
We're obviously talking high-level security measures.
Yes.
Let's assume that everybody out there manages to keep his Bitcoin safe, even if someone owns a quantum computer. Most of the public that uses Bitcoin wouldn't use these measures, and in case even somebody is affected by a quantum computer, the entire system would go down because of
Right. So there will definitely be at least some people that lose their money. So what we as a community can do is we as a community can promote wallets that only use every address once, which is what a lot of wallets do already. So if you have a wallet that only uses addresses once, then you're pretty much already safe against this. So it's basically just it's a matter of starting now to build good wallet software.
Yeah, the payment protocol that will be in Bitcoin Qt 0.9 will make people no longer need to work directly with addresses. So it will be easier for them not to reuse the addresses because it will generate them automatically, and the person will not publish his Bitcoin address. He will publish some sort of identifier which his client will take care to match to a new address each time.
And you said that blockchain info doesn't they use it only once.
Okay, blockchain.info maybe it's I mean they can do the same thing. I mean once we have this protocol as a standard.
Do you know if they already
No, they don't. Right now the default is that they use one address and that's it, but they can easily change that. And once you have the payment protocol as a standard, it will be easy for everyone to conform to it, all the world developers.
Okay, other? Yes.
I would like just to note that there is some cryptographic elements that are not based on elliptic tables and similar cryptography that are allegedly resisted to
Yes, I'm going to talk about those.
Enter you and all that.
Yes.
What about deterministic wallets?
Yes, so that's right, deterministic wallets. So, number one, election wallets. So the trick with election wallets is that there's two things to it, right? Number one is the way private keys are generated, and number two, there's this idea of a master public key, right? So with quantum computers, if you have a master public key, then you can figure out what all the private keys are. Now, on the other hand, if you have an election wallet and you don't tell anyone the master public key, which is what you do by default, then it should be entirely safe because the way that the election wallet generates private keys from the seed is using hashes, and hashes are still very hard to reverse. Yes.
Would it be maybe more like easier vulnerability to hack into people's computer and just take the information from
Actually, yes, that's a very good point. Yes.
In this scenario, what's to stop the attacker from just forking the blockchain and creating 10 blocks?
Right, so in that case, basically I'm assuming that everyone's going to have quantum computing. So if only one side has quantum computing, then it's extremely unfair and there's not much we can do about it. So hopefully if the NSA figures it out, we want Edwards movie to leak it. Otherwise, hopefully there'll be some open source university effort. With that'll give us plenty of warning. And yes?
When is such a computer expected to exist?
I believe this should tell you how long it'll take until such a computer exists. Not in the very near future. Some people are predicting 10 to 20 years, others are predicting 30 to 40 years, others even longer. It might not be practical. Yes?
How much are you predicting?
How much am I predicting until quantum computers?
March
maybe
2017.
Let's say maybe a 10% chance within a year, a 30% maybe like a 30% chance or so within a couple of decades, sort of anywhere up to middle or like the later parts of the century.
But isn't it that likely that the NSA already has such a computer?
Well, if Edward Snowden is to be believed, like his encryption is still completely safe. That's sort of all the security experts that I've talked to think that the NSA does not have any kind of magic backdoors into cryptography. Like there are some protocols at the end that are potentially problematic, but Bitcoin doesn't use any of them. Actually, and yeah.
Vitalik.
Yes.
Hypothetically speaking, if somebody from the future came to you and gave you like this super quantum computer today, what do you think the first thing you would do with it would be?
Open source it. So yes. So what are the advantages of this? So number one, I described that it's secure. Number two, it's fairly simple to implement. And number three, it doesn't really impose that many space requirements. Disadvantage, you don't have instant transactions. So you cannot send instant transactions to a merchant. So right now, for example, you can send transactions instantly. Like you can pay on any kind of online shop or at a restaurant, and they accept the transaction within 5 seconds, right? Here, that's not going to be possible. Like you're going to have to rely on statistics confirmations to provide security.
Right, Vitalik, I think we talked about earlier, I don't remember what was the conclusion. What if you use a micropayment channel with this? So maybe you can put the hash of some lower transaction.
Right, the problem is though, is that if you just put the hash, there's no way to prove that that hash actually contains any significant amount of money in it.
Oh, yeah, but no, in your direct communication with the receiver, you give
so
them
if you have direct,
transaction.
so if you do a direct communication with the receiver and you trust the receiver, then you can potentially even just give them a private key and.
Yeah, but okay, yeah, okay.
So. Here's another idea. So Lamport signatures, this is one of these quantum proof algorithms. So the nice thing about Lamport signatures, the reason why I like them, is because they rely only on hash algorithms, nothing else. Now there are other algorithms like Entru, for example. So Entru exists, it seems to be secure. So the problem is that number one, there's the legal issue, which is that Entru is still patented until 2016. And number two, I'm personally somewhat apprehensive, like potentially it might be possible that quantum computers might figure out some way of solving it later on. But the nice thing about hash algorithms is that hash algorithms have been shown to be secure against just about everything. Like hash algorithms don't have some sort of magic, some secret key where if you figure it out you can break it. It's basically hundreds of different things jumbled together all in one. So the pros is that with Lamport if you sort of replace elliptic curve cryptography with Lamport signatures and you get instant transactions, a weakness of Lamport signatures is that you can only use them once. But two things. Number one, you're going to be discarding addresses after each use anyway, so not a problem. Number two, there is a scheme called Merkle signatures that build on top of Lamport signatures to let you use them multiple times. And the other problem is that signatures take up quite a lot of memory. 3.2 kilobytes per signature in this case. So go get into somewhat how Lamport signatures work because I think it's really cool. So basically, start off with Lamport signature. You start off from some seed. It might be like 100 bytes of random data. It could be your password if you like brain wallets. It could be whatever. Then you expand that seed out into many pieces. Now here I'm showing 12. In reality, it's going to be 160 by 2. So 320. Then hash all of them. This is your private key. So you have 160 times 2 hashes. And then you hash everything there again. And you have 100, and then that's going to be your public key. So your public key will be basically 320 hashes. And these will probably be hash 160s so that you can't, that'll provide you with the 2B level of security. So what's the point of doing this? Well, first of all, we'll look at the signature algorithm. So basically you take your private key, then you take the message, then you hash the message. Then, from the hash of the message, you get some binary digits out, and then you use those for 160 binary digits and then you sort of to figure out, am I going to take the first part of every pair, or the second part? So here there's a 1, so I'm going to take the second one of the pair. Here there's a 0, so I'm going to take the first one. Here there's a 1, so I'm going to take the second one, and so forth. And then you publish it. So basically you're publishing half of your private key. So this is why you can only use it once, by the way. If you use it twice, then you're publishing 3/4 of your private key, and that's too much. So here, so you publish half your private key, but a precise half that depends on the message. So the signature is going to be public, and then if some attacker wants to create a signature for another message, they're not going to be able to, because the hash will have at least some binary digits that are different, and then so the signature is going to be different. So the attacker would need different parts of the private key. So, questions at this point?
Is this used anywhere, like now?
Is it used anywhere? At this point, not really, because the only practical reason why you might want to use Lamport signatures is for quantum safety. People aren't quantum paranoid just yet. So, and finally, verification. So, with verification, basically the idea is that you take the full public key, then you take your signature. Now remember, your signature is some specific half of the private key. So you hash it. You get a specific half of the public key, right? So from there, what you do is you take from the public key, you hash the message, and you get the exact same pattern of 1s and 0s that you got when the signer was signing the message. So you take the pieces from the same places of the public key that the signer took from the private key. And then you just check, are these equal or not? If they are equal, then yay, it verifies. If they're not equal, then not the right signature. So that's basically a high-level overview of how Lamport signatures work. And Merkle signatures, I'm not going to describe them here because it would just take. If I was going to get into the technical background of all of this would probably be half a university course, or probably a full one. So next, so how do we use these in a combined protocol? So here's what you might do. Send a transaction. In a transaction, you have your public key, the signature, and the transaction details. So a public key we already agreed was 160 times 2 times 160. Which is 25,600 bits, and the signature is half of that, 12,800 bits. Now the trick is that you can do some Clover compression. Basically, you send the signature and you won't send the other half of your public key. So if you do that, that'll get you down to about 6,400 bytes, and then another 100 bytes for the actual transaction. So you send that. And then miners do the same thing that they do now. They check that the signature matches the public key, and they check that the public key turns into the right address. So base 58 check right from D160, shed 56, that's just what I showed you way back here. So with Lamport signatures, the derivation will be the exact same, except that you would have 6.4 kilobytes here and 6.4 kilobytes here. Right. So, and then 120 blocks later, or whatever number of blocks later, the miners would forget the public key and the signature, and you have just a transaction. So here you have basically, as long as hash algorithms are safe, you can have this. And this protocol will allow instant transactions, because you can send transactions instantly, just like you did before. It saves space because the 6,400 bytes eventually are going to pretty quickly get forgotten, and it's quantum proof. So the one somewhat problem is that if the blockchain has a glitch that's more than 120 blocks long, then it might get problematic. In reality, though, the longest blockchain glitch we've ever had is about 90 blocks. So the chance of this happening is still very low, but it is potentially something to be worried about. If you want to have more security, then you might want to expand 120 to say 500. then you'll have to store a bit more data, but you'll have some more security. So, actually, before we get to this, are there any questions at this point? On Lamport signatures, protocols. Okay, everyone perfectly understands Lamport signatures and we're able to do it and be able to rewrite the algorithm for the text. Got it. Okay. So here's an interesting thing that's a group called Newsphere has been working on for the past year or so. The question is, can we simulate quantum computers on classical computers? Now, the answer is obviously we can, but the problem is that we have to keep track of every single possible part of the superposition. So if you have a superposition over 256 bits, you're going to have to keep track of 2 to the 256 different states, which will take you longer than the lifetime, or not longer than the lifetime of the universe, so long that the universe does not have enough entropy to complete the computation to do. Now, in 1998, there is a result called the Gauss-Mendel theorem, which is that some quantum circuits that use what's called Clifford gates, can be simulated faster. In 2004, there was a result from Bradley and Kitaev, which is a concept of magic states. And magic states potentially might let you do any kind of quantum computation using only Clifford gates. But the problem is that magic states can't be simulated efficiently. So there's still this exponential problem, but the problem sort of reducing these magic states. However, in Vol 2012, non-magic states might work, but you need error correction at every step. Problem with error correction? Error correction introduces an exponential blowup, so it's still exponential and it's still inefficient. Weinstein 2013. Error correction can be pushed to the end. Here, maybe this just might work. So,
what do you mean by error correction?
So basically, the idea is that with this protocol, right, you have magic states, and assuming these magic states can be simulated magically, you have magic states, and these magic states let you simulate any quantum circuit with this simulation-friendly circuit, right? So the idea here is that you use, instead of magic states, you use states that are themselves Gauss-Mendel friendly, but then, because those states aren't quite magic states, you do error correction at every step to sort of
adjust them to
to adjust everything. So this result is that all the error correction can be pushed to the end, and everything will magically work out. Maybe. So potentially, if all of this works and all of this can be put together the right way, maybe quantum cryptography can be efficiently simulated. Maybe. Newsphere thinks the answer is yes. Yeah.
Doesn't this simply mean that factorization isn't a hard problem if you can
Yes. This basically means that factorization and discrete logarithms and a lot of other things are not hard problems. So.
What is Newsphere? Is it a commercial company?
Yes, it's a fairly small startup based in Toronto. It's been sort of picking up over the last few months. There's been getting some investment at this point. So this is something you might potentially need to be scared about. Although then again, the other side of the argument is that, well, people have been trying to build perpetual motion machines for 1,000 years, and they've always, and it seemed a lot of the time like they're really close to succeeding, but there's always this energy conservation problem that you can push further away, but you can never get rid of. So maybe it's not actually possible, and all these tricks are just sort of pushing the inefficiency out further and further, but they can't get rid of it. Maybe. So, can we go stronger than quantum? So, Myron 1, there's a result that nonlinear quantum computers can do Grover's algorithm in n to the 1/4 time. What does n to the 1/4 mean? Essentially, it means that you can reverse 160-bit hashes in 2 to the 40 time. 2 to the 40 is 1.1 trillion, which is very easy. If this becomes possible, then Bitcoin will need to not only do this whole Lamport signature protocol, it will also need to expand things out to from 160 bits to 320 bits. So instead of your address being this long, your address is going to have to be roughly somewhere a bit longer than this. So, I mean, can we improve on that result? It seems like maybe the result could be improvable. So what if you could do Grover's algorithm in some time, not n to the 1/4, but the logarithm of n to some power? What that basically means is that literally means that p equals np. Now, I'm sure lots of people have heard of the p equals np problem. Basically what that means, it's just one of the greatest unsolved problems in mathematics. Basically the question is, given a problem for which you can verify a solution in polynomial time, so you can say quickly, given a problem you can quickly verify any solution, can you quickly find a solution? Most mathematicians think the answer is no. If you can do it this way, then the answer is yes. If you can do it this way, then almost all cryptography fails. Except for information theoretical cryptography. So information theoretic cryptography, if you've done any kind of research into cryptography, you might have heard of one-time pads. One-time pads are information theoretic. So what information theoretic cryptography means is that there is always some way in which the output could potentially be anything. So for example, with an encryption algorithm, if you have a 10 megabyte file and you have a 256-bit key, there's only 2 to the 256 different ways that file can be encrypted, right? So the idea is that if you have infinite computational power, you can just search through everything until you find the one file that has to be correct. With information theoretic crypto, if you use a one-time pad, then a file can be the encryption of anything. So no matter how much power you have, you can't decrypt. So there's something called Chenier's secret sharing scheme, which is where you split data among n servers, say n is 10, such that any k of them can reconstruct the data. So say maybe 5 out of 10. This is information theoretically secure. Can we use this sort of tiny vestige of cryptography that we have left to build a cryptocurrency? Maybe. Maybe not. There's some interesting research into that. Secure multi-party computation. Feel free to look it up yourself.
What is a nonlinear quantum?
Right. So what does a linear mean? Essentially, a linear is a very technical mathematical term. Basically, you see this equation here, right? By the way, there should be a note here. So basically, linear is basically the same as additive. So if you do a quantum computation on a superposition, then it's the same as the superposition. So yes, if you do a circuit on a superposition, it's the same as the superposition of the circuit on all the parts put together. So linearity basically means that you can take addition and you can sort of put addition outside the brackets. It's a really nice property for mathematical systems to have. With non-linearity basically means that you don't have this property, and so you potentially have a lot more freedom in the way you compute the different things. And so this over here is the end of my presentation. Any questions? Yes.
Don't we have bigger worries when
yes,
the computer will be so smart, they will be smarter than our brain?
Quite potentially, yes, actually. Although the problem is, though, is that even still, I'm not sure I'm not sure just how much power it will give us, because yes, computers will be extremely smart, but the hardest challenges in computing aren't really solving mathematical problems, they're actually defining problems. So, like, how do you even define the problem of figuring out, like, taking an image of a room and figuring out what the objects are? Like, it's not a sort of clean mathematical thing you can put into a theorem. So P equals NP would help computing a lot. It would help artificial intelligence, it would help medical computing, it would help scientific computing. But cryptography will actually affect far more than anything else.
Okay, so we're over time, so thanks to Vitalik, thank God for listening. He's not running away, so if you have more questions, you can ask him later. Now, those of you who haven't signed up yet to the Israel Bitcoin Meetup group, please do so to receive updates about the next events. And also we are handing out some aluminum coins and stickers you can check out on the table outside. So that's it. So thank you all. And, enjoy the rest of the evening.